Okay, in this video I'm going to go over the homework solution to our Castigliano homework that was due last week in MAE 3323, Tulsa edition fall 12 semester. And so those were problems 4-65, 66, 68, and 69 out of the Shigley version 9 textbook. And problem 4-65 says use Castigliano's theorem to verify the maximum deflection for the uniform. Let's go grab a little more for the uniformly loaded beam. Appendix table A-9. And let's give me a second. I got to move something else here. It's not going to let me move it. So how do I move this stuff over? That really is not good. Okay, beam 7 of table A-9. And so let me go there. And so the appendices, there's beam 3, 4, 5, 6. So beam 7 is simply supported, uniformly distributed load, and we're going to want to calculate the max deflection or the deflection at the center. And of course we're going to do that by placing a dummy load Q at the center. Let's place it in the downward direction. And in the end, we might be interested in comparing to this Y max quantity 5WL to the fourth over 384 EI. And so let's go take a look at the solution, but realize when we put the dummy load Q here, we are going to have to do statics on one side or another. And since this is a purely symmetric problem with Q in the middle, reaction 1 and reaction 2 are going to be equal to each other, and reaction 1 has to hold half of the total distributed load and has to hold half of Q. So we'll have that statics done basically. Also, we'll probably be measuring X positive, heading forward away from the left end, pointing toward the right, and we'll probably be looking left is the way I would do this thing. And so our moment at any point until we reach Q is going to be, as we move, say, to a point right here, if you can see where my cursor is, as we move to there, and if that's at location X, then our moment's going to be a WX squared over 2 kind of thing. So let's jump to the solution as presented in the solution manual. Should be right here. And we'll do a little bit of scrolling. And let's see. And I'm going to zoom out a little bit. Let's go to about 100%. So we're going to place a dummy load Q at the center. And so our static reaction is going to be WL over 2. W times L is the total distributed load plus Q over 2. And then our moment, as I said earlier, is going to be a reaction. I missed it actually. Reaction times X, we're going to call that positive. And the reaction is WL over 2 plus Q over 2. Okay, that multiplying by X, then minus a WX squared over 2 term. That's the moment at any value of X, moving away from the left and looking left. And of course we want the deflection at the midspan where we place the dummy load Q for that purpose. So we're going to take our partial of our moment equation with respect to Q. And that partial is going to be a is going to be an X over 2. On this screen, this looks like it's a minus sign, but it's not. Partial of M with respect to Q is a positive X over 2. At this point, we can set Q equal to 0, so that our moment is WL over 2 times X minus WX squared over 2. And so we will then take our moment with Q gone and the partial and put them together into our deflection integral. Y max is equal to the moment times the partial of M with respect to Q. Notice something important here. We're integrating from 0 to L over 2. Okay, that captures half the energy of the beam. To get the full energy of the beam, we'll multiply by 2. Now, why do I say integrating from 0 to the midspan captures half the energy of the beam? Because the beam is symmetric. So the energy of one side is going to be precisely the energy of the other side. Now that offers us a pretty nice advantage. Going back to the picture, imagine I've placed a Q right here. As I integrate over half the beam, I get to a point where Q is, but Q doesn't cause any moment when I get to the midspan. As long as I'm not going to the right of the midspan, then that Q that's sitting here doesn't appear in my moment equation other than coming in through the reactions. And so I'm fully justified in integrating half the length of the beam, calling that half the energy, and then multiplying by 2. So an integral over half the beam of M, partial of M with respect to Q, substituting q equals 0, okay, a 1 over EI term out here because that's what the equation says, and a 2 to double the energy of half the beam. And then for the moment, we'll plug in WL over 2 times x minus WX squared over 2. We're setting q equal to 0. That's what we have in brackets right here. And then we'll be multiplying by x over 2. That's the partial right here. The rest of it is simply do the algebra, do the calculus, do the integration, and see what falls out. And so we do the algebra to multiply x over 2 times each of these terms. We do notice that we can pull a w over 2 outside of this, so we'll end up with that w over 2 sitting over here. And these remaining terms, I'll let you double check that this is algebraically the same as this. It's simply algebra. And then integrating an x squared term and an x cubed term. We're going to get an x cubed term and an x fourth term. And then doing a little bit of simplification, we in fact get 5w over 384 EI. We get a positive value for that. And going back to look at the appendix, 5WL to the fourth over 384 EI. They have a minus sign. We had a positive sign. Did we have that L to the fourth term in our solution? Where did the L to the fourth go? Well, certainly when we plug in L over 2, we're going to get an L to the fourth term. I am missing that L to the fourth term. And I think he just left it off. I think there's a typo here. There should be a WL to the fourth right here. Oops. Okay. There's problem 4-65. Then moving to 4-66. Looking at what that problem statement was. It says go to beam 3 of appendix A-9. And so jumping to the appendix, beam 3, 6, 5, 4. Beam 3 is a cantilever with a uniform load. And again, we want to calculate the deflection at the end of that cantilevered beam. We'll place a dummy load there, dummy load Q, and we'll calculate the deflection there. And so what we'll probably do is set up our coordinate system so the end of the beam is at x equals 0. And x looking back to the left is going to be, so x moving positive to the left is going to be our coordinate direction, and we will always look right when we do that, so we don't have to do any statics right here. Let's see if that's what the author did in his solution. I sure hope it is. If not, we will adapt. Okay, it says place a fictitious force Q pointing downwards at the end. And let's see what he says. Use the variable x originating at the free end. Okay, and positive to the left. And so our moment with a load Q at the end is a QX, and he chose to call that one minus. Okay, so that sets the sign of our moments. If Q is pointing down and it has a moment of minus QX, then our distributed load also pointing downward would have a moment direction of minus WX squared over 2. And of course, the partial of this moment with respect to Q, to get the deflection at Q, is going to be a minus X. Could we have called both terms positive? Absolutely. Then this term would have come out positive, and so would all of these. But the product of the two in the end would have been the same. So now I'm going to take my moment, set Q equal to 0. And so here's my only moment term, and here's my partial term. So my deflection at the end of the beam is a 1 over EI. The integral over the entire length of the beam of the moment times the partial of the moment, with Q set equal to 0. And so looking at that, we have the moment is minus WX squared over 2. The partial is minus X. We combine the terms, integrate. We can pull the W, it's a constant, and we can pull the 2 outside the integral, so we have a W over 2 EI. And this thing leaves us an X cubed positive value. The 2 is already gone, and so that can be integrated. And when we do, we get a WL to the fourth over 8 EI. Let's see, how did that compare with the solution from the back of the book? WL to the fourth over 8 EI, but a sign change. So we match the back of the book, and that's problem number 2 from the homework, problem 66. Now looking at problem statement 68. 68 sends us to another problem that says solve problem 4-52 using Castigliano's theorem. So let's go find problem 52. Here is problem 52. We have a bar, which could have been a beam, but we're adding a support right here so that this bar can only deflect torsionally. It's isolated from any loads that are happening that would cause bending here. As long as we really ignore the bending effect of this tiny dimension right here, and are we even given that dimension? I don't see it. So since we weren't given it, I don't see a means for us to be able to calculate that tiny little bending. We would ignore that anyway. It is going to be so tiny. We're going to get torsion in this rod. Now this rod has 2 different sizes, which means we're going to get 2 different torsional pieces because the GJ term is different in each region. Then we're also going to get a bending downward of this bar. We have to add those 3 energy type terms together to come up with the total deflection of this beam. And so we'll just try to remember that each of these is a 0.2 long. Each of these bars is a 0.2 long, and even this one is a 0.2 long. So 0.2 will show up prominently, and we'll have 2 torsional terms and 1 bending term. And do note that the torque applied to these bars are a constant. It would be the force times this 0.2 meter distance. So the torque in here is a constant, the torque in there is a constant. That sure makes the integration really easy. But our bending moment when we choose our coordinate system will not be a constant. We'll probably measure our moments from the free end of this beam and move toward the left and look toward the right to write our moment equations. That's probably the way it's going to go. So let's look at adding all of these 3 terms up and coming up with a proper deflection for this thing. And so going to the solution, scrolling down, problem number 68, and let me scroll over a bit. It says, and I'm going to zoom out just a touch, I think you'll still be able to read it. The energy includes torsion in section AC and torsion in section CO, the big section, the small section, and bending in section AB. We're going to neglect any transverse shear. And so in region AB, where bending occurs, the moment is F times X, what you would expect when we measure X from the free end. And the partial of moment with respect to that load F, we don't need a dummy load because we actually have a load F there. Go back and look at the picture if you wish. But the partial of M with respect to F is X. That's going to get us set up for the bending part of the problem. In both sections AC and CO, the torque is the same. And the torque is force times that length of AB, which was a 0.2. And so the partial of the torque with respect to the force F is just the length of section AB. So in this case, we're going to write this as an energy problem. So our total energy is the energy of torsion. And we could have written this as an integral of torque squared over 2GJ, integrating over the length. But we know that the total angular deflection for a bar under torsion is T squared L over 2GJ. Go back and look that up. Okay, I'm sorry, that's our energy, and we wrote that earlier. Go back and look it up. But this is region AC. We have what it looks like exactly the same thing in the region that goes from C back to the wall, C to O, but there is a difference. This is G of region CO. This is G of region AC. But they're probably the same because they're the same material. But J in region AC is different than J in region CO, and that's what makes each of these terms different. Okay, and this L would be the length of each section of the beam. And then finally, we have our energy of bending as an N squared over 2EI in the region A to B, so integrating between 0 and the length of the region AB. This is the general thing, and now we need to take partials with respect to F. So where we have T squared right here, we're going to plug in FL. Okay, t squared right here. We plug in FL. We write out G and J appropriately. The moment squared is F times X. And we're actually not showing this being done as moment times partial. It looks like we're going to actually take the integral, take the partial of the total energy. Okay, and let's just see where this thing goes. And so our deflection is the partial of this total energy right here with respect to F. And so that would be the partial of this term with respect to F. Now the only place where F appears is in this T term. So we can actually use a chain rule and say that the partial of this term right here with respect to F is the partial of this term with respect to T times the partial of T with respect to F. Here is T, here's the partial. And so the partial of this term with respect to T is 2T times L over 2GJ. But then we need the partial of T with respect to F, which is right here, which is the length. And so we would plug that in. Here is the partial with respect to T. Here is our partial with respect to T, yes. Then times the partial of T with respect to F. Do it in 2 steps. Or if you want, plug in F times L for T and square it and just take the partial with respect to F. It all works out to be the same thing. Here is the partial of the energy term in the small diameter section. Here's the large diameter section of torsion. And here is the bending piece. And this one is now written as M times the partial of M over EI, where moment, remember, was F times X and the partial was X. So now we got to plug all this stuff in. And so eventually we will plug in what T is in terms of F. Doing this integral, moment written in terms of F, the moment was F times X, and then partial was another X. So this integral term here becomes fx squared term, which will become an fx cubed over 3 eventually. Just now go through the algebra. This is nothing but algebra. We do eventually substitute that torque is F times L, already being multiplied by an L, so doing all that appropriate substitution. The other thing we substitute for is that J for a circular section is pi d to the 4th over 32, but we've got a diameter of the AC section, and we've got a diameter of the CO section, but we still have a pi d to the 4th over 32, and that I in this EI term is pi d to the 4th over 64. So we make that substitution, and the rest is just algebra, crunch and crunch down to the deflection. And now finally, I guess this problem asks for stiffness. Stiffness is simply K, which is force over deflection. So here's our deflection equation. We'll take the force and divide by this thing, which means take the force and multiply by this thing raised to the -1 power. Now, this thing does not show force explicitly showing up, and in the end it shouldn't, because our deflection involved force, and force over deflection, the force actually cancels out, and we're left with something that simply involves geometry and material properties. Plug in all the numbers as given to us, and we get a -8.1 newtons per millimeter of stiffness. If we had plugged all the numbers in here, we could have gotten the actual deflection. Okay, this is all kind of messy looking. Just remember that we're taking 3 pieces, and maybe let's just go back and look at the picture again. Torsion in the big section, torsion in the small section, and bending in this short section. Add those 3 partials of energies up, come up with a deflection, and then of course stiffness is force over deflection. That takes care of that problem. Let's go back to problem number 69, which is the last one. Problem 69 says go back to problem 4-63, okay, and use Castigliano to solve for the deflection at the midspan of 4-63. So let's go look at 4-63 is here. What we have is a beam with a large diameter, or actually it's a shaft with a large diameter in the middle, 3 inches of small diameter on each end, with a distributed load applied all the way across the large section in the middle. And so to find the deflection in the middle, we will place a dummy load Q in the middle. We'll have to do some statics to find one or the other of the reactions. We don't have to find both. But notice our problem is symmetric again. And if we're wanting to calculate the deflection in the middle, then even Q keeps the problem symmetric. And if the problem is symmetric, I don't have to integrate energy all the way across the beam. I can just do energy halfway across the beam, and that gives me half the energy. And then I multiply by 2 to get the whole energy. It saves me just a little bit of work. And here's where it really saves work. With the dummy load Q in the middle, I would have to write a moment for region 1 until I hit Q. Then once my X goes past Q, I'd have to write a moment for region 2, which is different than the moment for region 1. And so I'd have piecewise 2 different integrals. If I use the symmetry, I only have to write one moment equation, take one partial, and do one integral, not 2. That makes it quite a bit easier. Okay, let's just remember some of these numbers, the 180 pounds per inch, 10 inches here, 3 inches here, which means to get to the middle, we have 3 plus half of 10. So the middle is 8 inches away from the left or from the right. So let's look at how this solution proceeds. Going to, yes, here. Okay, problem 4-69, I want to zoom in a little bit, make this a little bit easier to read. And so first thing we're doing is calculating I, the moment of inertia, for the small diameter. No, this is the large, small diameter, 1.375 pi d to the 4th over 64. And then we're calculating the moment of inertia for the large diameter piece, which has a diameter of 1.75. Okay, so small moment of inertia, large moment of inertia. We do place a fictitious force Q pointing downward at the midspan of the beam. And when we do our statics, the reaction at both the left and the right must be the same. So the reaction on the left is half the total distributed load. We have a distributed load of 180 pounds per inch times a span of 10 inches, but we divide by 2. That gives us a reaction piece of 900 right here. And then R1 also has to carry half of Q, Q over 2. So our reaction on the left and the right-hand side is 900 plus 0.5 Q. Now, we are still going to have to write I missed it earlier. We have to write 2 different moment equations for 2 different regions because of the small section and the large section. We don't have to write 4. That's where using symmetry will help us. So in the range 0 to 3, where we have no additional load being applied except the reaction, the moment is our reaction number 1, which is this, which is that, times X. And then the partial of this moment with respect to Q is going to be that 0.5 times X. 0.5 times X. Then in the next region, we have to have another region for 2 reasons. The loading changes. We now start turning on the distributed load, but also our moment of inertia changes. So our moment in that region is still the reaction on the left times X. It's identical to this. But then we bring in a negative direction moment, which is our distributed load. It's going to be a W times a distance squared over 2. So W is 180. Distance squared over 2 turns that 180 into a 90, and the 2 is gone. And the distance of the center point of the distributed load from our current X is an X minus 3 distance. Okay? And so it's a W over 2 times a distance squared. The partial of this moment with respect to Q remains the same. It's simply 0.5 times X. Now, because we're going to use symmetry, we don't need to let X go out beyond the Q. We'll just use symmetry. So by symmetry, we can use 2 times M times the partial of M, integrating between 0 and 8. But of course, we've got to break this one up into 2 different regions because of both moment of inertia and the moment equation. The I value changes. So we have a 1 over EI1, the small one, integrating from 0 to 3, where our moment equation applies. And our moment equation is simply 900x, because we set q equal to 0. So 900x times 0.5x should give a 450x squared. Let's see. 900x squared, but then times the 0.5. Where did the 0.5 go? This 2 that we had sitting here times the 0.5 that will bring out, because of the 2 and the 0.5 to cancel each other. I would rather have put 2 times 0.5 times 900 times x squared. That'd be a little bit more clear, but it is correct. Now, in region 2 of the beam, where the distributed load turns on and our moment of inertia gets bigger, it moves to I2. We'll be integrating from 3, where the load turns on, to the center of the beam, which is at 8, and that's going to be a moment of 900x minus 90 times this thing, 900x minus 90 times that thing, all of it multiplied by 0.5x. Well, there's the x piece, and that 0.5 went out and canceled that 2 again. Okay, and so we have to do this integral and that integral, and when we do, we're going to end up with what? This one's going to be involving x cubed over 3, but the 3 cancels the 900, etc. And this one is going to involve what? An x times an x times an x. Its highest power will also be an x cubed. And so, let's see, actually, did I say that right? No, sorry. This one involves an x squared integrated, becomes an x cubed over something. This one is going to involve a 900x, an x squared term here, times another x is an x cubed. We'll be integrating an x cubed and bring about an x to the 4th term. Here is that x to the 4th term. We still have to integrate this, here it is, but substitute the 3 and the 8 into it. And this one needs the 0 and the 3 substituted into the indefinite integral. Plug it all in, crunch the numbers, and we get the deflection at the midspan of this shaft. I'll leave it to you to see if these numbers flow to those numbers, flow to that number. And that ends this video explaining our homework for Castigliano that was due last week. Enjoy.